So, right. So one of the things that we did, I was doing on Wednesday, and because of using Vn plus and Vn minus, it ended up being more confusing than I intended. I did over the diagrams here, and we look at it, and hopefully that'll clear up the explanations for us, right? So this is put this on full screen here. Good. So this is the precision rectifier that we were discussing, and to determine what the output is when Vn is positive and when Vn is negative, all right? So the drawing here, the top diagram is when Vn is positive. When Vn is, in other words, we put up plus V. So that's how I'm looking at it. So we have a plus V. A plus V, if you go back here, because this is a non-inverting amplifier, a plus V forces A to go positive. All right, we'll see what the actual, where it lands up in a second. But once A goes positive, dP starts to conduct and dN is reverse bias. So the equivalent circuit, instead of dP, we have a short circuit on the connecting the output of op-amp 1 back to the inverting input. So we have V plus here, and let's analyze what the output is going to be now. If V plus is at the positive input or the non-inverting input of op-amp 1, point A is also V plus. So here becomes V plus because of the virtual earth nature of op-amp 1. Same thing here. We have V plus on op-amp 2 here. And the virtual earth behavior means that point B also becomes, let me stop using the same thing again, plus V, right? So we have plus V, we have plus V, and we have V is plus V, right? Whatever that is. It's a precision rectifier, so we know it's a little positive voltage at this point in time. So look at what happens. If point A is at plus V and the other end of the resistor is grounded, there's a current flow in the resistor of I1, which is simply V plus V over R. But if you look at the points between A and B, if A is at plus V and B is at plus V, there's no voltage drop here across these two resistors. So in other words, the current flow through the two resistors is 0. So that current here is just going to circulate from V plus into that resistor and ground, through the op-amp, of course, and into the resistor and ground. So there's no current flow in the across these two resistors. This current into the op-amp is 0 for all intents and purposes. So therefore, we have no current going this way either. Nothing flowing here, nothing flowing inside of here. There's no current going in any direction between B and C. Therefore, the voltage drop across the 2R resistor is also 0. Therefore, if B is at plus V and you have no voltage drop across the 2R resistor, the output here, C, is going to be at plus V as well. All right? So plus V in, we get plus V out. Simple by how the fact that what we have done basically with plus V is that we've created a voltage chain with no voltage drop across the resistors. There no current flow through the resistors, so therefore no voltage drop across the resistors at all. So C is at plus V. Yeah? Make sense?
So it have the potential divider we are now.
Sorry?
And it have a way we could put it in the form of a potential divider and solve it to get the output voltage.
Right, but the output voltage as here is that if you look, if you have plus V here, right, and you have no current flowing through any of these three resistors, right, as a potential divider. Let's see if you have it. How many resistors we have? 4, right? But you have current, you have plus V here, and you have plus V here, and this is at ground, right? So if I have plus V here, all the current is going to go this way. Nothing could go in this way because you have the no potential difference across the 3 resistors. So that's basically it, and this is point C here, right? I've put another plus V here actually. This is plus V from op amp 1. This is plus V from op amp 2. So we have a current flow here, right? This is point A. If I redraw it, this is point B here. Yeah. So if I put a voltage of plus V on A and a voltage of plus V on B, no current can flow through here. Yeah. All the current going from A to ground, nothing flowing from A to B, and therefore nothing going from B to C either. So here has to be at plus V as well because you have no voltage drop across here. Right? Same explanation. So C is equal to plus V. Yeah? Right. Let's put minus V on it now. If we put minus V on the input, then A is at minus V and B is at minus V because of the virtual earth behaviors. All right? In this case, however, look at what happens. If A is at minus V and B is at ground, we have a current flow according to this green line here. Nothing goes into the op amp, so the current through R is now going into R1. Sorry, is now going into this resistor here. So the voltage at point D is the same current flow, which is minus V over R, that's the current here, right, which is going in here, multiplied by R, so that's the voltage drop across this, plus the voltage that you're starting with, which ends up with point D being at minus 2 volts. The other way we could look at it is what I said in class last time. If you look at it from this way, that is your basic non-inverting amplifier. The non-inverting amplifier gain is 1 plus R over R, right, which is equal to 2. And if the input is minus V, then the output is going to be minus 2V at here, right? So you can look at it either way. Here is the explanation without going through the op amp gain, but you know that already. Let's look at point B now. Point B is at minus V. Point D is at minus 2V. So that the current now coming through these resistors here, the current flow through this resistor, I2, is the voltage at B minus the voltage at D divided by R. So that is minus V minus 2V over R, which is giving you plus V over R, right? So that's the current through this resistor, which is also, because nothing is flowing here, that is the current is going to come from the output of the op amp back that way. So therefore, VC here is the voltage at B plus whatever voltage drop we have across the 2R resistor, which is I2, which is plus V over R by the value of the resistance. So that gives you minus V plus 2V, which gives you a plus V on the output here. So for a negative V input, we're getting a plus V coming out here again. The previous input, a positive input giving me a positive V coming out. A negative V is giving me a negative V, a positive V coming out as well. So in other words, we have a full wave rectifying behavior coming out. We just analyze it with DC, but understand this is 0 to negative V. the output is going to give me 0 to positive V here. All right? Make more sense now?
So when the two input is negative, right? Since it is, we're treating it as a non-inverting amplifier, right?
Which one are you
So
talking about? Here?
the second amplifier.
Mm-hmm.
Yeah, right? We're treating that as a non-inverting amplifier.
Yeah, but except that you're now dealing with a non-inverting amplifier where one of the inputs, instead of this input being grounded, the normal non-inverting amplifier is this sort of configuration where you have the input coming here, but the inverting end, we have this grounded. That's a normal sort of configuration for the non-inverting amplifier. In this case, the second one, we don't have this grounded. We actually have a minus 2V here, right? And we're putting a minus V here, right? So if that's the case, if that's minus 2V, and it means that this is minus V, and then if this is minus V and this is minus 2V, the current flow is this way. So therefore, because this is not taking any current, the current has to be coming from the output. All right, so that here has to be more positive than here, which is more positive than here. All right, and so that whatever current is here is V minus 2V over R, which is this, multiplied by this one, which is 2R. So that gives you a drop of plus 2V here. Here is minus V, so therefore here has to be minus V plus 2V, which is plus V, right?
Yeah.
Everybody see that now?
So I have an expression, right?
Yeah.
You see at point B, right? It's going to have any current going through to the negative side of the terminal.
No, you remember we're assuming ideal op amps, but this is for all intents approximately 0. Typically, it is in the small microamp to nanoamp range, right? But for all intents and purposes, remember for op amps, one of the assumptions is that the input currents are 0. All right? Remember that? Input currents are 0, input impedance is infinity, output impedance is 0, all those kind of things. So those are characteristics of the ideal op amps. If it's non-ideal, then you have a few microamperes or nanoamperes. But compared to what is flowing elsewhere in the circuit, that you could neglect that. All right? So the main thing is that the output of the op amp driving the feeding the current. So this particular op amp, has to sink I1 plus I2 through it, right? So that current is going into here, and we'll go back to the negative voltage that you're putting in. That's how it will work, right? Or to the power supply.
Right. So both inputs for the second amplifier, right? It's going to be negative, right?
Yeah. Because of the virtual load. So you have where my pointer. You have minus V here, and you have minus V here. Right, which is why B is at minus V.
And C will be positive.
C is positive V, correct.
So the oldest reason that it does work as a full wave is because of the 2R and the current the current flowing in that direction. If it was just R, the voltage would be 0. And if
correct. So if you put R 0 inside of there, then the system will behave like a half-wave rectifier.
And if it was that, I think this is R. If R3 was 2R and R4 was just
R3, which is R3? Which is R3?
The one between D and B.
Yeah.
If that was 2, No, the one after. Yeah. No,
Mhm.
the one before that. If that was 2R and the one after was R, then you would have the current flowing forwards and it would be negative
Negative.
V at the output.
Yeah, so
So
you're not
the
getting
only
you wouldn't get any rectification.
so Camerage, like although it's a non-inverting amplifier, the only reason that it have full wave is because depends just because R3 is R and R4 is 2R.
Mhm. Yeah. And in fact, now you know that. So you could actually, if you increase the gain of this, sorry, if you increase the value of this to 3R, for instance, you could actually get a amplification on the positive on this output, right? So you could actually make the rectification. We know that when the input is positive, okay, so there's the input here, all right? Let me get a different color for the output. We know from this side, when the input is positive, the output is positive. So here, when the input is positive, the output going to be positive. Here now, when the input is negative, with 2R, the output is going to be, is doing that, the output is going to be this here. If I change that to R, we get nothing. And if I change it to something bigger than 2R, I can actually get it doing something like this. Once this is less than VSAT for the op-amp, right? So you could get a kind of asymmetrical rectification going on here. That not serving too much of a purpose, but if that is what you want, you could actually change the value of at least that half, the negative half cycle rectifying. So you'll get something looking like that, right? And in fact, if you were to use not ideal components, real components, let's say this is 1K and this was supposed to be 2K, but you're dealing with 5% resistors, right? And it just so happened that this is 1K minus 5% and this is 2K plus 5%. Then when you look at it on the waveform, you might actually get something looking like this. It's kind of looking asymmetrical, and then you're wondering, wait a minute, the theory saying is supposed to be equal, right? So
You get 10% extra.
Exactly, and you just raised an important point, which is something that we wouldn't see here, but you see it in the lab. So somebody gives you're actually given a waveform looking like this. So you build a waveform and you're getting this. You build a full wave precision rectifier and you're getting something looking like that. What is the explanation for that behavior? That explanation would be that this value is not 2R, okay, which is a practical thing. So sometimes you land up with these kind of situations and you have to address it as well. But the explanation now, is that a little bit clearer?
So what does I think tire people is because it's a non-inverting amplifier, and when the voltage input is negative V, you kind of expect the output to be negative V as well.
Right. It is, we are putting the inputs on the non-inverting. Okay, so we go back to here now, right? We are putting the inputs on the non-inverting input of the amplifiers to get high impedance. That is where the high impedance part comes in. All right. Depending on the behavior of these diodes, when this one, when this one is open circuit and this one shorts out, in other words, when this one is off and this one is on, we actually have this bit, that amplifier, behaving like a perfect non-inverting amplifier. This one is more like a non-inverting amplifier, non-inverting summing amplifier, right? You remember what a summing amplifier does? You have a voltage at each of the inputs via a resistor, and you want to figure out what the output is doing. So your normal summing amplifier would have been this kind of thing that oops. right? You put V1 and you put V2 here, right? You have a feedback resistor here. So this was R1, R2, let me put this back here, RF, right? This was a sort of summing amplifier that you're accustomed dealing with, right? And the output was minus the sum of V1 and V2 if you made all the resistors equal and so on, right? We have a similar thing here, except that we have one voltage, and then instead of grounding this, I'm putting another voltage here, right? So you have to treat it, instead of doing it, it's not working as an inverting amplifier here. It's kind of working more like a summing amplifier with some gain on it. All right. And once you understand that, and the easiest way to understand it is to forget the op amp. The only thing you have to realize with the op amp is that it takes no current coming in here. So what is the current flow? Whatever comes out of the op amp either goes back into the circuit, is going one or two ways. It's either going towards the output, is either sinking current or sourcing current from the output of the op amp. And you work from there. Yeah?
So one question, just to refresh my memory, what does happen if it have two voltages on the two inputs of our op amp?
If an op amp is like this, right? If you put a V1 here and a V2 here, right? The output of the op amp is going to, the op amp here is working like a differential amplifier. So the output here is going to be V2 minus V1. All right? It's working as a differential amplifier. Of course, because the gain of this is so huge, any small difference between those two is going to send this either positive saturated or negative saturated immediately. So typically what we do is to put some gain resistors to make, instead of the open loop gain, you remember a open loop for all intents of an op amp is nearly infinity. So we put some feedback and gong resistors here so that the closed loop gain is now something finite. And once that is done, then the op amp produces a difference of the voltages of the two inputs. Right? This is on the lecture with differential amplifiers and instrumentation amplifiers. It's clear inside here.
Okay, thanks, sir.
Right? All right, so we're all right with that, right? Make some sense? I hope it's a little bit clearer now. Okay, and I'll in our own discussions later on and in future, I'll know sort of how to approach it for the class. Okay, so let's let me just stop that. And what I want to talk now about is just quickly, let's review one of the last topics that we did. It came up in the exam paper. So I'll just run through some of the things that we did on active filters so that at least you have that review as well. And it also answers, hopefully will answer some questions that wait a minute, let me stop sharing here. Just now, let me try to get that. Right, okay, let me try and share the screen now. Hopefully you'll see that. Active filters 1. Are you all seeing that?
Yeah.
Right, I had a blank screen for a while. I don't know why that happened. All right, okay, good. Right, we spoke about some of this when we were on Wednesday, right? So characteristics of the filters, the main types, we described that just in general, some sort of frequency ranges for filters and so on. What we're dealing with op amps here, active filters, So those, the upper frequency for the filters is normally a couple hundred kilohertz maximum. Unless you have very specialized op amps, you wouldn't tend to get responses going much higher than that. These are sort of the parameters. All filters have a pass band and a stop band and so on. There's the characteristics here. And sort of the ideal filters that we're dealing with. And the filters, well, you know, again, all of these things, all electronics really are described by differential equations. Right? From the time you have a RC or RLC circuit, you're going to have a differential equation inside of there. Right? It may be a first order, it may be a second order. So again, we use the tools that we learn. Instead of dealing with the differential equations, we deal with the differential equations in a domain where they're easy to handle, which is the S domain. So you normally take the Laplace transform of that. And what that gives you is an expression that describes the behavior of the filter in terms of two polynomials in S. And we know all of this thing, the roots of the polynomial, the poles and zeros, determine the transfer function behavior, the frequency response. And we spoke about that in signals and systems. Some of you all who are doing it would have just done it, some of that today. Others who have done it before, remember when we were talking about that. The poles and zeros determine the order of the response, how fast it decreases or increases with frequency. All right. And then we went into a discussion here on, for instance, first off, a low pass filter. What is a low pass filter? As I said, it passes frequencies between DC and up to some cutoff. Right. Now this cutoff could be fairly high. I mean, there are low pass filters that could go up to the hundreds of kilohertz. But once it's passing from DC to that, that's low pass. Okay, even if the upper frequency is quote unquote high. The fact that it is passing everything less than that means it's a low pass. Okay, and this thing, the cutoff frequency of a filter is also called the 3 decibel frequency. You know that from some other stuff. In other words, if you're looking at the response of the filter, as soon as the response, once this is in a dB scale, as soon as the response drops by 3 dB from whatever the flat or the flat part of the response was, that is what we determine as the cutoff frequency. And remember, 3 dB is really the half power point. So it means that whatever is passing through the filter is now half the power that it had before. Right? And we also know from signals and systems that that cutoff, we sometimes call the corner frequency or the break frequency of it. Okay? High pass filters, as we say, does the opposite. So it starts at some cutoff frequency and it goes above that. All right? And you can have, again, you can have something like 10 hertz and it's passing everything above 10 hertz. Although this is low, because it's passing everything from 10 hertz and above, it is a high pass filter. Okay? So the actual value of the cutoff frequency is not so as important as what the filter does. Right? From the cutoff frequency, if it is passing things less than the cutoff frequency, then it's a low pass. If it's passing things more than the cutoff frequency, then it is a high pass. And then, of course, we have the band pass, which produces, which allows things within a band to get through and stops everything else. These are the kind, this and the notch, which the notch, the band stop, or the band reject frequency does the opposite. It gets rid of a particular set of frequency, but lets everything else pass. Right? These two are typically used in conjunction with each other to treat things like in audio systems, equalizers. Right? And equalizers are a set of bandpass filters. All right. Sometimes they also have band stop or notch filters with them. For instance, this is the one that you would use if like you have an audio system and you're having feedback, you're getting some sort of feedback from a sound source or a microphone or something, then you could put a band stop at that particular frequency and get rid of it. Or you're in the lab, because we have a power system that has 60 hertz signals in them, a lot of times when you're taking measurements in the lab, there is a 60 hertz signal because of the electromagnetic field that we are in that is corrupting the signal there. So sometimes you have to have a filter that will just simply take out that 60 hertz signal alone and let everything pass. Okay, so those are the sort of typical applications for the filters, right? And then we had a discussion on the transfer functions of the filters. A simple RC circuit in this configuration where you have the input and the capacitor, the ground, acts as a low pass filter. And you could kind of understand why. Forget the op amp for the time being. What is the reactance of a capacitor at low frequency? The reactance of a capacitor at low frequency is what? Low or high?
Capacitors block high frequency, right?
That's the question I'm asking. Is the reactance of a capacitor
Low, I believe.
right?
I think so.
Right. A capacitor, and you know the formula for the reactance of a capacitor. At low frequencies, the reactance of a capacitor is very high. At high frequencies, it is very low. So at low frequencies, this is a high impedance. In other words, this behaves like an open circuit, so that most of the signal goes through. As the frequency starts to go up, this resistance, the reactance of this starts to get less and less. So in other words, more of the signal starts to go this way. And at very high frequencies, now the capacitor reactance is very low. It's a short circuit at high frequencies, more or less, so that most of the signal will be going here and nothing go here. So that now is a low pass type of behavior. If you were to look at the output here, at low frequencies, the capacitor is letting things pass. At high frequencies, it starts to short off V out. So V out slowly decreases as the frequency goes out. Right? This is low pass behavior. But to compensate for losses and so on, we put an op amp in the circuit. Right? It's a unity gain amplifier, but what it does, it provides a very high input impedance here. Because if I just have a simple RC network and I connect this to some other circuit, whatever is the input impedance of this circuit now starts to appear in parallel with the capacitor and loads it. The input impedance of our op amp, remember, is big, right? Is normally in the tens of megohms kind of thing, right? So it's a buffer. That's what a unity gain amplifier is. This is a high it behaves as a high impedance buffer, right? And then you could work out, so the transfer function, VO, so VO is really this VO because there's a buffer here, right? Normal voltage divider, the frequency transfer function, of course, is substitute 1 over S equal to J omega. And we have defined the passband as the point where the magnitude of this is 1 over root 2, right? That's a 3 decibel point. So 0.707 of the passband value, right? What will give this, what would make this 0.707 of the passband value is when omega c is 1 over RC, right? And there's a typical response of it. Right, so all that is fair, is basic circuit analysis and so on, right? And you could plot it like you, this is a single, one capacitor is a single pole. So this goes at minus 20 dB per decade, right? We had a discussion of that. The transfer function looks like this, 1 over SCR, so that's a simple pole, right? Okay, and of course the phase response similarly. Right, and we discussed this elsewhere, the log scale, decibel scale, and so on. If you want to put gain on the op amp, then you can, instead of just having the input like that as unity gain, you can put some resistors feedback. Resistors are feedback and ground resistor on it, and you're using the high input impedance here, right? It's non-inverting, and you now have a gain, so you could compensate for losses as well. So this is a filter with gain, right? Same cutoff frequency in either radians or in hertz. The high pass filter, now you swap the resistor and the capacitor, and you can understand why. So at low frequencies, this is a high impedance, almost an open circuit. So at low frequencies, nothing getting through, right? So if you have the low frequency, at low frequencies, nothing gets through. But as the frequency starts to go up now, this slowly starts to conduct, the reactance of this starts to get smaller and smaller, so that as the frequency goes up now, V out, which is here, starts to get bigger and bigger and bigger until, right? So you get that sort of behavior, which is the high pass behavior. Okay? And I guess and the transfer function, of course, now for a high pass filter has both a zero and a pole in it. No. So how does that work? So this is the response here. And again, from your Bode plots, if you know a zero, the response of a zero is to increase from at plus 20 dB per decade. All right, and then the response of a pole is to decrease at minus 20 dB per decade. Right? So if you add the two of them, right, what you will get is a response. If I were to add those two, which is just a little revision for the, if I were to add those two where response, what you would get is this going all the way up until this point, because before here is 0 plus 20 dB, so the frequency response is going to go all the way up. And then after this point, you have plus 20 dB, minus 20 dB, so the response is going to level off, right? Which is high pass filter behavior. Right, so you could predict it from that as well, without plotting anything out. That's why we did things like a Bode plot and so on in signals as well. Right, and then you could show some gain on it again, like we did before. So it's the same, what do you call it, high pass response, and you're putting some gain on it. All right, so that was straightforward. Everybody remember that? Hopefully you did. All right, and then where we took it now is that we went from first order to second order. And while we were doing that, we were saying is that sometimes that the first order transition, in other words, this 20 dB per decade may be too slow, right? Because you realize what happens. If this is my cutoff frequency here, the 3 dB cutoff, right, it's still passing a lot of frequency components even beyond the cutoff. The ideal, you remember, is supposed to look like this. Once you hit the cutoff, it stops everything. The first order passes quite a bit, right? If you look at the actual plot here, you notice that even though even the cutoff point, the 0.707 point here is right there. Notice that what do you call it? Is still plotting. Sorry, still passing a considerable amount. Really and truly, what we wanted it to do was this, right? It's nearly impossible to get that, but if you could get this thick red line, right, this is more like what we would need. To get that, you need to add more poles, right? Need more poles in the transfer function, right? Remember, each pole gives you 20 dB per decade. So one pole gives you plus 20, two poles gives you plus 40, three poles give you plus 60, and so on. That's the cutoff. So the slope of the cutoff keeps getting more and more. So let's add one more pole to that. One more pole means for the low pass filter that we need to add another capacitor. And how we add the capacitor this time is we take the original, this is the first order system here. We add another resistor on the input and we add a capacitor now on the output of it. Okay? This one is a little more complicated to analyze, so this should be C1 here. Right, so we have two new poles now. And notice where the input here, so we need to calculate VB. VB is what is going through we need to calculate, V out is the output here, but we need to calculate both VA and VB in terms of V out and VN. All right, the actual input to the op amp is VB. And this was a simple calculation, simple circuit theory inside of here. Just like we did this morning for the amplifier, right? So VN minus VA, right? So that's a current here over R1, right? That current is going, we have a current node here. So the current here has to be the current going, which is VB, VA minus VB over R2, and VA minus V0 over Z1. And then remember, you have to eliminate both A and B. So you have a relationship between A and B here in Z1 and Z2. Okay? And then you now make use of the fact that because of the feedback, the virtual earth here, this is actually V out. So now we can start substituting back inside of there. And if you do it, it takes a little while, right? And it's something that I'd like you to try for your revision, is to do this and show that the transfer function is this. It takes a little bit of juggling around to get to that. Make sure you don't mix up to keep the subscripts, sorry, going all the way through. And eventually you get it down into this point. And of course, the frequency response is to substitute S equal to J omega, and you have it here. Now, to make the filter practical, we have to use some resistor values. So we let R1 and R2 be equal, and we let C1 be twice C2. Right, and you pick a value for that. And when you do that, the circuit simplifies into a fairly easy form. And the cutoff frequency, of course, is when the magnitude of this is 1 over root 2. And if you do that, of course, you can substitute, you can solve, and you get that omega is root 2 over 2 RC, right? Or sometimes you would see it as 1 over root 2 RC. Why I don't like this particular version is that sometimes people forget and put it like this, 1 over root 2 C, right? Which is wrong. Right, so this one is a little bit, this here is a little bit less error prone, if you remember it, root 2 over 2 RC. Okay, so your revision task when you're looking at this going to be to do the algebra. Make sure you get it, get that particular answer here. Of course, you could put gain on it. We'll get to that in a little while. This is what we call the Sallen-Key amplifier, Sallen-Key filter, right? This is the most common type of op-amp filter that you're going to encounter, and is a particular type that we call a Butterworth. There are other types that is not part of our syllabus here. And sometimes you see this term of voltage control, voltage source amplifier. Right, it is a unity gain filter because we have we're just using the op amp as a buffer inside of here. All right. Okay, and here is a little revision question. So if this is the sort of response you get, if it was a third order filter, then you would get it at decaying at minus 60. And this is a typical response. If you compare this to the slides in the other lecture that we just looked at, you'll see the difference in slope. This is minus 40 here. The one early on would have given you minus 20. So we're getting closer here. And how we design it typically is, of course, if you're designing a filter, the first thing somebody has to tell you is, or you have to know, is what is the cutoff frequency, right? Once you know the cutoff frequency, then you start to work from there. You choose, the next step is to choose C2, right? And you choose some value. It's a trial and error, but it's easier because capacitors, you have less choice in the sort of values of capacitors. You tend to choose a capacitor first, and you choose a value where you know you could get a double. Capacitors come in certain values and so on, so you make sure you could get one that is twice the value of the one that you choose. So if you choose 1 microfarad, you could get a 2. Those kind of numbers, you could get 5, you could get 10, and the like. And then once you know that, you calculate, you let R1 and R2, they are equal, so you could calculate their values and work out. If this is getting too big, you remember you don't want, typically, you want about a maximum of about 1 megohm here for these op amps, right? And a maximum here, maybe 10 microfarads, right? Right? We have a good guide here as 1 microfarad, but you generally don't want to go beyond 10 microfarads for these two, right? So you pick, and if you find, if whatever value you chose here is giving you too much of a, too big a resistor, then change this and go back and recalculate the value of the resistor again to try and get a smaller one, right? And then we actually did some of this morning as well. Remember the second order transfer function. So you could compare and see, if you compare the two transfer functions here, we just derived this. This is the standard transfer function here, right? If we let A equal to 1 because a unity filter, a unity gain filter, and then divide it out with omega equal to 1 over root 2 RC, then you could kind of see how the coefficients look inside of here, right? And then if you want gain, same sort of thing. But the gain, normally, there's a little thing here. So you don't normally want to put the gain for more than 3. We're not discussing stability in this course at all, but there are some reasons. What happens is that if the gain on this gets too high, then the behavior of the feedback circuit doesn't work too well, and you start to get some instability in the filter. Okay, so typically you would want to keep the gain in the filter by itself loop. Usually the better procedure is to do this, and then have a second amplifier where you have the gain here, right? So keep this as a unity gain and then put a second amplifier with a gain instead of trying to do both the filter response and the gain in one device. Okay, that's just good design protocol there, right? The high pass filter, you swap the capacitors and resistors again, all right? And this one, the general form of the transfer function is going to be in this, because it's a second order, remember, because it's a high pass, you have poles and zeros. So now, like in the first order high pass with something like a 1 over 1 plus S kind of arrangement, this now is going to have an S squared over S squared plus something going on. So you have 2 poles and 2 zeros in it, right? By swapping the capacitors. And then in the Sallen-Key function, if this is the general form of the high-pass transfer function, we didn't derive this, but it's fairly easy to do, all right? In the case of to create the Sallen-Key function, the coefficient A1 is √2 and B1 is 1. So you get it into this form here, right? And then back to the circuit, you could sort of derive it out here and then compare and rearrange and compare it with the standard form to see what you get. Okay? So again, this is the hardest part here, to get this particular form. It's fairly straightforward, but you have to take your time to do, right? And I would suggest again that you do it as part of the sort of revision for here and for future. All right? So K equal to 1 is a unity gain, and you could compare the responses here. All right. And this is the sort of response here. This, of course, is plus 40 dB per decade, whereas what do you call it? Single, for the first order filter, would have had something at plus 20 dB per decade, right? And if it has 2 zeros and 2 poles, 2 zeros would be increasing at plus 40, 2 poles would be decreasing at plus 40. So if you add the 2 of them, you get this sort of behavior that we did, this sort of behavior here. Okay, so this is another point that I like to try to make here. Don't disconnect what you learn in one course from what you learn in another. Right? If I give you a second order transfer function, you could draw on what you learned in signals to help you sketch out the response here. All right. This one, again, same thing. If you have a high pass filter, of course, somebody have to tell you what the cutoff frequency is. Then you choose the capacitor values, and then you calculate the resistances again. All right. Again, you can add gain. All right. Again, not more than 3. Right. The better process is to design this and put the gain amplifier afterwards. So it's not part of the filter circuit. Yeah. Right. And then we have one more little filter thing which had to do with the bandpass and notch. And I'll talk about that on Monday. Please go ahead and answer some questions. Somebody have put there's some questions on the spreadsheet about relating to bandpass and notch filters and so on. So I will take it up there. Right. But essentially now, as I said on Wednesday, you all have to be trying the papers, trying the past paper questions and letting me know now what is making sense and what isn't, so that I could clarify those matters and make sure that when you get the exam that you understand everything. All right. So any questions? That was a quick review.
For one of the when you designing the pump, right? I'm probably going to figure out the capacitor like for C1. I realize for one of the slide they had C1 equal to 2C2 and one of the other type of pump can let it be that the C1 equal to C2. Like how you gonna figure out that?
Just now, let me see which one that would have been. Hold on, let me just look back and see if I can get that slide here. Right. This one? Right. So this actually, where are we? Let me see. Right. So in this one, to simplify the transfer function, that was where this particular relationship happened. If you don't, then you get a transfer function that has two capacitors and two resistors, each of different values in here. What turns out is that if they, and this has to do with network synthesis and frequency response behaviors. We didn't get into it here. But if you make if you make C1 twice C2, the transfer function here simplifies into this form here. All right? When you're doing the high pass filter, right? Right. For the high pass filter, this time you set the two capacitors equal, but the resistors, one has to be twice the value of the other one in order to simplify the transfer function into a workable form. If we didn't have that relationship, then we're not going to get this sort of frequency response behavior that you're dealing with. So in the low pass filter, the capacitors, one has to be twice the value of the other one. In the high pass filter, one resistor has to be twice the value of the other one. Yeah. But as in order to get the transfer function into a form where we only need one R and one C. Other than that, you have to work with this. Right? Yeah?
Yeah.
All right. So any other questions? Okay, so I'll stop the recording here.